Hello. We're doing our last topic for the quarter. Last new topic anyway. The rest of the quarter is exams basically and the project. There was a question in the chat about the homework. Which ones are the end of the homework? So the last homework, I just opened it up, so you probably haven't seen it, or at least not open. And it's homework 22. That's the last one. There is a 23, but we're not doing that one. 22 is the last one. And they're all, I think everything that's left is due either Wednesday or Thursday of next week. And it's 19, 20, 21, and 22 are still open, plus the optional ones, the optional and the SA. I don't remember what SA stood for, but whatever that stood for, the super problems. The SA ones are the bonus ones. The optional OP are just optional practice. So 22 is the last one that we will cover, and it is today's topic. Today's topic is a really short topic, so that's not going to take very long. So if you have questions about anything, let me know, and we can work on those. But let's do today's topic. Today is the topic of stress concentrations. So we've been calculating stress since like the first week or whatever, 10 weeks ago, 9 weeks ago, whatever that it was. And what we've been doing is calculating like an average stress. So let's look at this. So we've done things like the axial stress in a bar. Maybe it has a plate with a hole in it or whatever it is, but we've done some of those types of calculations, and we did things like this. So here's a really simple one where we've got a bar of some sort, and there's some kind of axial force on the bar. Maybe let's just put numbers in here. So this is 200 pounds, and then let's say that this bar is, let's make it half an inch wide, and we'll just go ahead and write here, we'll say that it's 1/8 of an inch thick. So it's a rectangular cross section. What we did is we went and said that, well, we can calculate the axial stress. Stress is defined to be whatever force divided by a cross-sectional area. So we said sigma equals force over area, and for this setup, it would be the internal force. Let's see, I guess I should make sure that we have the reactive 200 pounds over there, so it's not confusing that it's not a static problem. So our internal force here would be 200 pounds, and our cross-sectional area would be 0.5 inches times 0.125 inches, and that's some number. Let me get my calculator out. Let's see, 200 divided by 0.5 and 0.125. So like 3,200 psi. And what this stress is this is the well-developed stress in the middle of the bar somewhere. So if we were able to draw like a stress intensity plot, or maybe put this into SolidWorks or one of our finite element simulation packages, and we could go in and simulate this, then what we get is some kind of stress profile where it's really high stress is out here, and then somewhere, near the middle of the bar, I get this kind of evened out stress profile. So that 3,200 psi that we calculated is, it's somewhere over here. But there can be other areas in the bar, in the plate, whatever it is we're dealing with, that have an actually higher stress than this 3,200, or even a lower stress, depending on how it's made and shaped. But we haven't been calculating that. And so what this idea of stress concentration factors what it attempts to do is to go in give us a manual way, so I don't have to go put it into a finite element package or anything. I don't have to do any simulations. I can do it by hand. It gives me a manual way that I can go in and estimate these higher stresses based on what we're going to call stress risers. Now, what I've drawn here is more like the effect of having a point load applied at a single infinitely small point. But what we're going to talk about as far as our stress concentration factors is the idea of stress risers. So for us, what a stress riser is going to be, the stress risers could be something, they're pretty simple. In fact, I could probably generalize them to the stress riser is anytime I have a change in geometry of the part. So it goes from big to little, or it's got a sharp corner, or something like that. That's going to be a stress riser. It's got a hole in the middle of it. So those are going to be the areas where I would probably have a higher stress than the number I've been calculating. So the average stress I've been calculating is going to be lower than the higher stress near one of these stress risers. So change in geometry is a stress riser. A sharp corner associated with that change in geometry, or maybe a hole punched out of the part that would also change the geometry. So in general, I'm changing the geometry somehow, and near that change in geometry is going to be a stress riser, and the more abrupt the change in geometry, the higher the stress riser, the stress concentration factor. Oh yeah, on Canvas it only lists up to homework 21. I literally like 2 minutes, well no, I guess 8 minutes ago now, changed it to include the 22. So that would be a very recent change. The 22 is the topic for today, so that's why I forgot to include that one. All right, so let's just, there's not a really, well, we can draw one more picture, I suppose, just to kind of give you an idea of what this would be. So the classic one, and I think it's even the first one we'll work a problem about, is you've got some kind of tab. So maybe something like this. And it's going to go down to a smaller area over here. And I haven't included the corner yet. So the worst case situation here is I make a really sharp corner. So that sharp corner is going to have a really high stress concentration factor. So if you think about the way the stress has to flow through the object, for our objects that we've been dealing with, they're just kind of longitudinal, or they're pretty straight. And so the stress has a direct path to develop throughout the whole thing equally. But if I've got, let's put a distributed load over here to avoid the situation of the point load and its stress concentration. We're going to ignore that. So let's say that this is kind of how I'm loading this thing, and it's in equilibrium and all those sort of things. Then what you could imagine is, actually let's put the same number of arrows on both of these if I can. I think I have 8. 1, 2, 3, 4, 5. Let's put one more arrow in here. Maybe we can kind of center those up better. There we go. So how this will work with this sharp corner is that, you know, this stress has to flow somewhere like that. And then this one has to do something like this. And this one has to do something like this. So what that does is, in this area right here, and the same thing on the mirror side, I just didn't draw all of them. that area, stress flow, the way the stress has to flow from the bigger side to the smaller side, gets tighter and tighter. It's compressed. And with a sharper corner, the more compression of that flow I get. These are all kind of abstract terms and ideas, but it's trying to describe what's going on in here. And so I'm going to have a stress riser at that corner. That corner is going to be a stress riser. And in order to make this a better transition, I'll do, well, let's not make that a sharp corner. Let's round it out some. So this feature is a fillet. So not a fillet. Fillet is for fish, things like that. This is a fillet. And what it does is it gives a little bit more gradual transition from the large side of our tab to the smaller side. And so when these stress flow lines have to compress, it just gives them a little bit more room to not get so bunched up. You know, they're still going to have an increase. It's still going to be bunched up a little bit, but it gives them a little bit smoother transition. So there's still a stress riser there. It's just lessened by rounding out or filleting this corner. So that's a good habit to once you're actually designing your own parts and making your own CAD models or whatever. In general, you don't want sharp corners for a couple of reasons. This is one of them. One of the sharp corner problems is that it does create higher stress concentrations at that corner. The other thing is that sharp corners are hard to make. You know, a lot of your, maybe if you're laser cutting some flat piece like this might be, then okay, you could probably get a relatively sharp corner. But if you're using any kind of milling, subtractive process like that, then getting a sharp corner is actually kind of hard to do. So, or expensive. Maybe you can get it done, but it's more expensive to do. So it not only makes manufacturing the thing simpler, but it reduces these stress risers, these stress concentration factors. So I think the first problem we're going to do, so yeah, like your dog bone simulation lab, that's lab 1, right? Where I gave you kind of freedom to make whatever kind of dog bone specimen you wanted to do in SolidWorks. There is a standard, so I think I did link or maybe told you the ASTM standard shape for the dog bone specimen, and so that shape has kind of been optimized to reduce as much as possible these stress concentration factors. But if you made your own, you might have put a really sharp corner at the transition from the gripping part to the gauge area of the sample, and it would create a really high stress right there at that corner, and that's not really what you're trying to measure in the tensile test. And so you might have ended up with some simulations that gave you the stresses kind of being the highest at that transition, and you were really wanting to know something else. So yes, it's like those dog bone shapes. That's why they have that fillet in there, and it's pretty extreme. So these fillets don't have to be huge, but they do help. The larger the fillet that you can still have your design do all of its other things, the better. But there are reasons, if this is a shaft, think about this being a round shaft now, and I've got some gear blank or bearing or something that has to go up against this corner, then I can't make the corner very sharp because the bearing has to go up against it, and so that's going to give some clearance problems. So there's always this limit on what you can do, but the general idea is that sharp corners are going to be bad for manufacturing and going to be bad for stress concentrations, and the more round, the more filleted you can make your corners, then probably going to be better off. Let's go over to web work. Is there any situation when you would want a sharp corner? Well, yeah, so like I was talking about, maybe for a round shaft, let's see, how would I... So we haven't we did talk about shafts, you know, a little bit. And in power transmission in general. So this is a shaft now. Even though it looks exactly like the other one I was thinking was like a 2D plate. This one's a round shaft, and so there's a torque or whatever, you know, applied to it. There are many shafts where they're stepped. So most of what we did, the shaft was just like a rod that's all the same diameter, which is also common. But a lot of times the shafts are larger in the middle, and as they get closer to the ends, they step down and down and down for various reasons. But what will happen is I might need to support this shaft with a bearing. So let me find a picture of what kind of bearing I'm talking about. So one of these guys. So I might have to support it with one of these. Did that show up on your screen? Yes, they did. All right. And so that bearing might sit right here. You know, it's got this ball bearings inside there, and it's 2 pieces, all that kind of stuff. And it's holding the shaft up while also being relatively low friction. And so if I wanted to put a ball bearing against this edge of the shaft, then I can't put a really giant fillet in here, because now the ball bearing is going to get wedged in there. It's going to not be straight. So I'm limited on how much fillet I could put in there. And you can kind of see, let's look at this one. I think you can see it pretty well on this one. Where's the picture? There we go. So you can kind of see that darker edge right there. That's the relief for the fillet to fit in, so that this bearing can go up against the shoulder, the larger part of the shaft, without first bottoming out on that fillet. So, but that's all you get. So usually one of the pieces of information, I guess, on this data sheet is going to be that clearance. Now I'm not seeing it right now. Oh, look right there. Max fillet radius 0.12. These are probably, I guess, inches. Yeah, there's inches. So 0.12, 12 thousandths of an inch radius is the maximum fillet I could put on a shaft if I wanted to use that particular ball bearing or whatever kind of bearing I have. So there is a reason at some point where you can't just put this really, really sweeping fillet, because you're limited on by your application of where it needs to go. All right, so let's go look at some of these problems. These problems are really straightforward. Web work, they are a little bit tricky in web work because there's a little bit of estimation involved. So this is, let's do optional 3, probably somewhere in the 15, 16, nope, we did that one last time. Here's one. All right, so this is basically what we just described previously, where we had the 2D tab that's, maybe it's laser cut or whatever, I don't know, but this one has dimensions on it. We also have a chart like this. There, I looked up stress concentration factor charts, and you know, there's all kinds of charts. All kinds of charts. So in your exam reference, we have maybe 3 charts that we're going to look at, but this is one of them. So it's a little bit crooked, so we'll deal with that, but it'd be nicer if the chart was straight. But it didn't. It's not. So what this says is this is a little bit of a reverse problem. So instead of calculating the stress, we're going to figure out how much load we can put on this tab without exceeding some kind of stress value. So why don't we work on this problem? And see what we can do. So we want to find the largest axial load P. So they've got P labeled here, kind of like we had it labeled. Safely supported by a flat steel bar. So steel, different materials do behave differently to these things. So some materials are way more brittle. Steels are way more ductile. So they do give a little bit versus just snapping in half. So that's probably why this says steel bar, although it doesn't give us a particular type of steel to go find the material properties. It just tells us here's the ultimate strength. So it's two areas. It's all some portions, but the thick or well, the wide and the narrow areas, both are 10 millimeters thick, so that's shown on our picture. And then they give us the width, they give us the fillet radius. Assume the material is brittle. So this one is brittle. Okay, so the ductile materials, they'll kind of deform a little bit to kind of even out some of the stress concentrations. And so that's not part of what we're going to try and calculate. We're just going to straight up calculate based on our charts here. We need a factor of safety of 1.4, and we've got some ultimate strength. So first thing, let's just find our allowable stress. So our allowable stress is in this case it says ultimate strength, sigma u, divided by our factor of safety. So 249.5 megapascals is the ultimate strength, and we're going to divide by 1.4. So a lot of times we've been using the yield strength or the elastic strength. Since this one's brittle, it's more likely to fail just by fracture. So it doesn't have a whole lot of plasticity to it, or it doesn't, once it starts deforming, it pretty much breaks because it's brittle. In fact, that's what this number here is telling me. That's percent elongation. So it means that it doesn't stretch a whole lot before it just snaps in half. So that's what this is kind of telling me. You don't have to have that kind of level of, well, is this brittle or is this ductile? That's not going to affect our problems. Our problems are going to work directly like what we're doing here. But once you get into more complicated situations and your depth of understanding is deeper, then you will have some considerations to make on the stress concentrations and risers and stuff like that for brittle versus ductile materials. All right, so 249.5 divided by 1.4. So we're going to allow 178.2, and then again, this is web work, and we're going to have to read off this chart. So how much to round, I don't know. Hopefully it's got a lot of tolerance built into this problem, but this is what we're going to go with. That's how much we're going to allow. So looking at our little diagram here, the worst case of what we've been doing would be, all right, well, that area, somewhere in that the thinner part or the more narrow part, that's where the stress would be higher. So the first thing you do is you just calculate the stress like you normally would. So if I cut it open where I've shown that little diagram, then I would have P. I don't know the value for P, but that's the force that I'm trying to figure out. And the internal force there is also P. So the internal force is P. And if I calculate the stress there, sigma equals P over A. Okay. P is equal to, I don't know, area is equal to, let's put them in meters. So the thickness is 10 millimeters, 0.01 meters, and the width is 40 millimeters, 0.04 meters. Okay, so that would be the stress I would normally calculate. But I know that, well, the closer I get to this fillet, the little radius, then I am going to experience some stress rising. So the stress is going to multiply by some number. That number is on this y-axis of the chart. It's named K. So if I need to multiply this thing times that number, and the number K, the stress concentration factor, so the stress concentration factor is directly related to the geometry. So it's built on the, how large is that radius, how big of a section am I coming from and going to, and all this kind of stuff. So how it works is, first of all, I have to find which one of these lines, which one of these traces on my little plot do I need to be on. And it looks like they are related, so the trace equals D over lowercase d. And then I have to look at my picture. I've got, you know, one that looks like this. This same chart works with a plate with a hole in the middle of it. It just gets its own line. You know, there's a circular hole line. So for me, uppercase D looks like it's labeled to be 60 millimeters. Lowercase d for me is 40 millimeters. So that gives me 60 divided by 40 is 1.5. So that means I'm going to be on, let's do this. Which one of these lines? This line. Okay. So you just find which line you're on. If you, so for hopefully for us, oh, what is a trace? A trace is just, it's one of the lines on a multi-plot line or graph. So if you have a graph with a whole bunch of lines on it like this one of those lines is a trace. So it's you have whatever term, it does not important that you call it a trace. That's what I call it, and I think that probably goes back to one of the older MathCAD versions. That's what they called it. But that's what I'm referring to, is you've got to choose which one of these lines, which one of these graphs you're going to follow, and you choose that based on this ratio of wider area to narrow area. Not the area, but the width of them. One thing about this particular chart is that it does assume that the thickness, this 10 millimeter, well, I've got two 10 millimeters, the thickness here is constant. So it does assume that. Okay. So I'm on the line I colored blue. Then I go and figure out, well, where am I at on my x-axis? So for me, I have the ratio of R over D. That's going to be my x position. And my fillet is shown to be 10 millimeters. Lowercase d is 40 millimeters. So I've got 10 divided by 40 is 0.25 or 0.25, and that's going to get me to right here. So now it's just a matter of reading the chart. This one's set up really nicely because look, it perfectly intersects where k equals 1.6. So they don't always work out so nice and perfect. This being a homework problem works out a lot nicer. So for me, k equals the number 1.6. That's the multiplying effect of this fillet. If the fillet was sharper, so if the radius gets smaller and smaller, then you can see that radius to dx value gets smaller and smaller, and I get moved further to the left on my chart. At some point, it just gets basically infinite, you know. It maxes out, my graph maxes out at 3, but it really takes off exponentially once I get to the really sharp corners. All right, so I've got my information now. I've got my stress concentration factor. I've got an equation for K. I know my allowable stress. So what I end up solving is sigma allowable equals whatever your stress concentration factor is times the equation that you would normally use. So this equation, I'd normally use P over A or F over A. I wrote a P up there, so I'll write P here because I think it's labeled P is the axial force there. So let's plug in what we know. I know my allowable stress is 178.2 times 10 to the 6 pascals. K appears to be 1.6. I don't know how much force I can apply. And my area, based on my geometry that the problem gives me, is that. And the only unknown in there is P. So I should be able to solve for the maximum value of P that I can apply to this little tab without exceeding this strength, while considering the fact that the stress is going to be higher at that fillet. So let's see. 178 million. Oh, 178.2. divided by 1.6 times 0.01 times 0.04 quantity. 44,000. These would be newtons, because remember, a Pascal is a newton per meter squared. So newtons are what's built in there. So let's see if 44,500 gets us any. Oh, well, this is in kilonewtons, so 44.5. Was it 5.5? 5.5. Yes, correct. All right. Let's do another one just to have a different one. Okay, so this one is a bar with a notch in it. They give us a they give us the little graph. It's a lot tighter, you know, between the different lines on our graph, but let's work on this one. All right, the beam shown is subjected to 180 newtons. It has these grooves 10 millimeters deep, cut into the beam at a 0.1 meter from where the load is applied. Determine the smallest allowable width of the grooves. So the width of the groove is this dimension. That's what they want to know. If, again, they give us allowable stress. So this one, they just tell us the allowable stress instead of giving us a strength and a factor of safety. So they just straight up said, well, allowable stress, 150 megapascals. Okay. Neglect the effect of shear stress due to bending. We have not done anything that combines shear and flexural stress. We haven't done any of that. So that's consistent with what we've been doing in this course already. So this is a beam, cantilever beam, in bending. So what we're going to need to do is, I don't know if you remember or not, but sigma equals m times c over I. Remember, we technically had a negative sign in there. I'm not going to worry about the negative. That's not going to be the point of what we're doing. So MC over I. They give us a chart over here to figure out the value based on actually the same two factors we had before. They're just labeled, you know, a little bit different here. So let's see what we've got. So D over D. For us, that is, according to their picture, let's see, 60 millimeters. I'm looking now, you know, I'm looking over here to get most of this information. Lowercase d is supposed to be, well, 60 minus 10, so 40. So that's our same ratio we had last time, I think, isn't it? 1.5. So we're on the 1.5 line, which is here. I think it's this one. Okay, we're on that one. And then R over D, the radius, well, so they give us actually 2R is the width of the thing. That's actually what we want to solve for. So looks like we're going to have to figure out what K can we use and kind of back our way into what R is going to be. So we don't know, we just know which trace we're on, but we don't know our radius. So we're going to have to figure out how we're going to get that. So we've got our stress equation for a beam in bending. So M, let's work on M. So some of this stuff might be, you know, we have to recall, how do I solve a beam in a cantilever beam with a point load on the end of it? How do I do a flexural stress equation? So that was stuff we did last time, last exam 2, not last lecture. M is going to be, we need the moment at this cross section, so we need to actually cut this, you know, right there. And if we did that, what we would have, a free body diagram would look like this. We have a point load over here, Do we know that value? Yes, 180 newtons. We have this, which is 1 meter. And then we have our internal shear force. It told us to neglect the effect of shear, so we don't need that. And there's our internal bending moment. If we do summation of moments about the cut, I would get M plus 180 newtons times 1 meter equals 0. So M equals negative 180 Newton meters. And again, the negative is not going to really matter too much on this as far as is this a positive moment or negative moment. We're not really worried about that. Some materials do behave differently in tension and compression, but I have no reason to believe this material behaves differently in tension or compression. Okay, so we have M. C. So remember, you have to go back to your flexural stress equation. C is the distance from the neutral axis to the point of interest. So they actually, well, look at this. They actually even show us a picture right here. So this is our side view, kind of the end view of our cross section. These little areas here, why they're showing that is that's basically the edge of our little groove, and it even labels. There's the value of C, and that is what we need for C. So that distance is 20 millimeters. So hopefully you can see, here, 20 millimeters, 20 millimeters, and then 10. So C is going to be 20 millimeters. So let's put that in O2 meters, just to keep our units straight. You could get a little confused on this one. But since I've cut these notches, I'm going to use that as the area where I want to calculate I versus the whole width of the whole thing, the 60 millimeters. So I'm going to only use that red part as I. It is a rectangle. So again, if you don't remember the moment of inertia equation, you have to go look that up. I do happen to remember BH cubed over 12 is the moment of inertia of a rectangle about its own centroid or its own neutral axis. I'm assuming that this little green line that I've drawn here, that's the neutral axis, and it's all symmetric, so I don't have to go find the centroid. So this problem could get more complicated if I had all of that to deal with. But here the base, look, they even labeled it the right way again. Base is B, 9 millimeters. So again, I'm going to put that in cubed over 12. So let's see what that is. So super tiny number, 4.8 times 10 to the negative 8th. But those units are meters to the 4th. So if you kept it in millimeters, then it'd be a giant number. But since we're in meters, it's a really tiny number. Okay. So now I've got all the numbers I can plug in for M. And I've got a value that I can plug in for sigma. And I have most of what I can plug in for K, so I can calculate K using what I know, and then I can go back to my stress concentration chart, find that value for K, and figure out what the radius needs to be. So let's do all that. So sigma let's write it down. Sigma equals M times C over I. Sometimes we have my over I. C is just the largest value you can put in there for y. So they gave me an allowable stress, 150 megapascals. Oh, times K, because we do have the stress concentration factor. M was 180 Newton meters. Technically it's negative, and there's a negative sign, you know, so I have two negatives, so it comes out positive. C is 02 meters. I is that really small number. And K is the thing I want to solve for. So K is going to equal, and hopefully it comes out to a nice number on our chart, but let's find out. 150 million times 4.8 times 10 to the negative 8th divided by 180 Newton meters and divided by 0.02. So I get, came out really nice. I got K equals 2. Let's see if that's what they want. So if K equals 2, that intersects my blue D over D line right here, and I get R over D is equal to 0.1. So R, the ratio of R over D equals 0.1 equals R over lowercase d is, well, that was 40 millimeters. And therefore, R must equal 0.1 times 40, 4 millimeters. That's not quite what the problem asked for, though, because if we go back way up here, I drew this a long time ago, it actually wants us to know the whole width of our little groove. So R is only half of that. The width of the groove is R times 2, 8 millimeters. So hopefully, web work, it seems it came out really even and nice, so I'm going to think that this is probably right, but let's check and see. It is correct. So that one is way more involved. You know, we're trying to work backwards, and we're dealing with this. Got to remember the beam stress equation, all this kind of stuff. So these can fall. I assume the next problem is actually a torsion one. Yes, it's a torsion one. So it works exactly the same, except this one, you know, you're dealing with the power associated with it. So they can get more, you know, technical in the sense of, I got to remember a beam stress equation, or you've got to remember a power equation or something like that, or the axial stress equation like the first one we did. But basically the general idea is that you calculate the way we've done the whole time. Yes, I just multiplied the radius by 2 because they even show it here, right here, that 2R, and on WebWork I think it said 2R equals 8 millimeters. Yes, so the radius, and you can kind of see up here where R is shown to be the radius of the fillet. And so the width of the groove is 2 radiuses, because normally that's not true, but this is like groove that's cut into the bar. Normally a fillet is just 1 radius, but this one has 2 sides since it's a groove. So the general idea, you calculate like you've been doing the base stress, the average stress. So either force divided by area, or MC over I, or T rho over J, you know, whatever, TC over J, whatever your base stress is. And then you multiply that stress by a stress concentration factor, which you get from one of these charts and knowing the geometry of your part. And that's your new stress. That's your stress that would be located at that stress concentration factor. So they're pretty straightforward. This one's a little more involved because we had to go do the beam stress thing and all that and kind of work a little bit backwards on it. There's probably one of these, not necessarily this style. I would think the one on the exam is going to be more this style. But there's probably one of these on exam 3. And it should be pretty straightforward on solving these. You've got a couple of homework problems that are basically like this. In homework 23, they might be the exact same problems. I don't know. But homework, not 23, 22. Homework 22. Homework 23 is not assigned, in case you missed that earlier. Homework 23 is one of these things, but doing in SolidWorks. But we've done SolidWorks in Lab 1, Lab 2, and your project, so I don't feel like we need to do a homework on SolidWorks. What would you recommend studying for exam 2 retake? So the retakes, they're not the exact same exam, but they are the same idea. So the exact same type of thing. Some of the questions could be the same, particularly the content questions like identify the 2 force members. For exam 2 would have that on it. So it's going to have the same problems types. There'll just be different pictures and different numbers. But you'll still be solving a frame, or you'll still be doing a flexural stress. It just might be a different beam or different numbers on the beam or something like that. So I would study the things that you missed and review the things that you got right, just so you don't accidentally miss one of the easy ones. But I would review the stuff that you missed on exam 2. I should have exam 2 like finished up before you have to actually take the redo. So you can go back. I assume you can still see exam 2 though, right? It's not closed down. Yeah, well, so I did figure out the problem, but the formatting issue on exam 2, there's one problem that was just really messed up. I figured out why it's that way, but I can't fix it, so that problem's just void. So it doesn't matter what you put on that problem, you got it right. I think it was only 4 points anyway. So yeah, I don't remember what problem number that was, but there's one that I even had to go back on it and wrote not to attempt it because it wasn't going to be something I could fix during the exam. But I know what went wrong. All right, so that's all of stress concentration. That's actually all of the whole quarter. No more content. So unless you have a particular question or something, I'll send out Zoom links on Monday for the retakes. Again, we'll have noon and 7. You only get to do one of them, so pick one and do that. And then I'll send out the Zoom links on Wednesday for exam 3. I haven't had any person ask in Moodle or not Moodle, in Canvas or Discord or email about groups, so I assume everyone has a group. I have had some people ask about like not 3 or 4 person groups, and I've replied to that, but I haven't had anybody seeking a group. Could you explain the number of teeth and how? Oh yeah. So our grades on exam 2 reflect that mess. So the grades on exam 2, they will. I haven't gone in and do that. Basically, you'll just get that credit because there's no way you could have answered it. So because it wasn't even set up as a question, really. It didn't have any place for you to put stuff, I don't think. So your grades in exam 2, once I put your grades out there, then they'll still be out of the 106, but remember, it's just like exam 1 where if you make whatever your number is, 96, you made a 96, then it's not 96 out of 106, it's a 96. So there are extra points, but I don't think Canvas is able to not calculate a percent, but what you want is just the total number. Your grades will actually be calculated in Excel instead of in Canvas. So the teeth thing, so that goes back to the power transmission. So if we go back actually a couple of problems here, that should be one. Oh well, that's the pressure vessels. Oh, there was one. Go to that one. So actually this one is N1 and N2. We started this one once and did part of it. So the number of teeth have to do with the gear ratios. So if we imagine two gears, oh well, let's do them this way. So here's one gear, it's got a bunch of teeth on it, and then it is mating with another gear that is a different size. So I'm just drawing them as circles, but they could have teeth on them that actually interface with one another, mesh with one another. But it doesn't matter for what we're thinking of. It doesn't matter if I think of these as cylinders that are touching each other and they have some diameter, or if they have some number of gear teeth on them, or whatever. It's all the same effect. So the effect is that maybe this is N1 and it is 20 teeth. And this guy is N2 and it's got to be more teeth, because the teeth have to match. I can't have little teeth on one gear and big teeth on another one and expect them to mesh together. So the gear teeth, the module of the gear teeth, they have to match up so that they can interface with one another. And gear 2 here is clearly bigger, so it's got to have more teeth. And let's just say that it has 60 teeth. So, and it doesn't matter if I tell you teeth or diameter or radius. That ratio is all going to be the same. So if the diameter of gear 1 is 2 inches, then the diameter of gear 2 has to be 6 inches, because it has to be the same ratio. Diameters have to be the same ratio. Teeth have to be the same ratio. Radius has to be the same ratio. All those ratios have to be the same in order for the gear teeth to actually mesh together. And if this guy has torque 1 equal to, let's put it somewhere else so it doesn't overlap everything. Torque 1 equals 100 inch-pounds, and it's going 20 RPM, revolutions per minute. So it's delivering 100, or it's inputting 100 inch-pounds of torque, and it's spinning 20 revolutions per minute. So one thing that happens here is that this gear has to turn the other way, right? Because the way, and it doesn't actually matter for what we're doing, but if they are meshed together, then one gear turns the other gear the opposite direction. Okay, so that's not, it is important, but not for our content. So this one, since it is larger, if you think about, let's just put a point right here on gear 1. That point goes around here, whatever that path is. Then on this gear, it's only gone to, something like there. It hasn't made it all the way a complete circle around, even though on the smaller gear, it's going a whole revolution. The bigger gear takes more revolutions, takes more turns of the small gear to get one revolution out of the big gear, and that ratio is your number of teeth or your number of diameter or radius or whatever. So this gear, if the little one is spinning 20 RPMs, I probably should have picked better numbers, then the bigger one's going slower, right? Because I turned the little gear 1 revolution, and the big gear's only going around 1/3 of a revolution. So 20, well, let's see. Let's do the math. RPM of gear 1 to RPM, of gear 2 is equal to the ratio of, there are 20 teeth on gear 1 and 60 teeth on gear 2. Maybe let's do it 2 to 1, so it'll work easier in my head. So there we go, 2 to 1. That will be number of teeth on gear 2 to the number of teeth on gear 1. So RPM of gear 2, I don't know, over RPM of gear 1 is 20 RPM, revolutions per minute. The number of teeth on gear 2 is 60 teeth. Number of gear teeth on gear 1 is 20 teeth. So I have a 3-to-1 ratio. 6 to 2 is same as 3 to 1. Oh, wait, I did it backwards. Oh, shoot. Sorry. That's what I was trying to avoid. 1/2. There we go. So when I do the math here, the RPM of gear 2 is equal to my 20 RPM gear 1 times 1/3. There's 20 divided by 3 is 6.7. So it's going a third slower. Whatever the ratio of either diameter, radius, or teeth, whatever that ratio is, the larger gear is turning slower. So that's why I don't ever actually remember, where do you put the 2s and 1s? I don't remember that. I just know that, well, the big one's going slower because it's bigger. So that's, I always do it just mentally without writing it down. That's why I wrote it backwards. But why you do this, there's 2 reasons, well, at least 2 reasons to do it. One of them is it does change the direction, and so sometimes you need the other shaft to go a different direction, clockwise versus counterclockwise. But the real reason, or the main reason, is that I've slowed down that shaft, the bigger one, but I've multiplied the torque by the same ratio. So the torque in gear 2 compared to the torque in gear 1, it is multiplied by whatever this is, my 3-to-1 ratio. So I guess it would be torque 2 over torque 1, or not torque, in. And again, I don't always remember where the 2s and 1s go. I just remember that the bigger gear is going to have a multiplied torque. It's going slower by some factor, gear ratio factor, but it's multiplied the torque by that same factor. So the gain is that it's going slower, but I've got more torque. So torque 2, I don't know. Torque 1 is 100 inch-pounds. And then N2 is 60 teeth. And the N1 is 20 teeth. Therefore, the torque delivered by the bigger gear T2 is equal to 100 inch-pounds times my 3-to-1 gear ratio, 300 inch-pounds. So I've slowed it down, but I've multiplied the torque. And that's generally the case. It's not always. I think this webwork problem actually has it the other way, where you're doing the opposite, right? So in one, the bigger gear is driving the smaller gear. Normally it's the other way. The smaller gear drives the bigger, or the smaller pinion, so the smaller one's called the pinion, is driving the gear, but this one's kind of backwards from that. And you're slowing down the output shaft, so in this case you're doing the opposite, but you're multiplying the torque. So this one, the picture here, the big gear is the one that's driving the smaller one. It's connected to the motor. The smaller one's being driven by the big gear, so that smaller one is having to spin around multiple times faster. Whatever N2-to-1 is, what is that? 100 to 10. So it's 10 times faster. So it's sped up, but it has divided the torque. So whatever torque N1 was delivering is divided by 10 in this case. But it's sped up a lot. Power, a separate thing, power is the same. That's the crazy part, is that it's the same amount of power, but it's just delivered at a higher speed with a lower torque, versus what we did over here, where if the smaller gear is the input, then same amount of power going into the little gear and coming out of the big gear, same amount of power, but it's delivered at a slower speed and a higher torque. So it depends on your application. Do you need a slower speed? Do you need a faster speed? Do you need lower torque so that your shafts don't crumble? Do you need a higher? Can you deliver a higher torque? So you have to decide those things when you're designing the layout of your shafts and the gears and all that. But the general idea is that the small gear or the small pinion, usually it's a pinion, that's just a name for it though. The pinion drives a larger gear, and it makes the larger gear turn slower but deliver more torque, and that ratio is your gear ratio, the number of teeth on the little to the number of teeth on the big. So that's the general idea. And there probably will be one problem, one of the more complicated problems, I guess, one of the ones that's more challenging, that has to do with gear ratios on exam 3. So our grades for exam 2 will reflect that messed up. Oh yeah, I already answered that. All right. Anything else before we close it down? And I can still answer stuff in Discord and email and all that kind of stuff too. All of these homeworks are due. I think you've got 2 that are due on Wednesday and 2 that are due on Thursday next week. And like I was saying earlier, I haven't heard anybody that doesn't have a project group, but you do need to make sure you have a group. It does, I think it's a whole letter grade, so you can't just ignore it unless you want a whole letter grade lower. I don't see any questions in the chat other than what we've already talked about. So I will see y'all on Monday. Well, maybe not. If you're not doing a retake, then I'll see you on Wednesday for sure. All right. See you either Monday or Wednesday or both. And hopefully it all works out really well for y'all. See you then.